Goedemorgen allemaal, welkom bij het webinar Analytics in de gezondheidszorg. Deze webinar is georganiseerd door Quister in samenwerking met Oracle. En bedankt voor jullie aanwezigheid. Een overzichtje van wat we vandaag gaan bespreken. Het werd net al even weergegeven in het filmpje. We hebben een korte introductie waar we de onderdelen even gaan toelichten en natuurlijk ook de personen. Daar geven we ook een korte toelichting op de waarde van analytics. De demo komt natuurlijk voorbij met de use case. En aan het einde hebben we nog even tijd voor vragen. Links bovenin zie je al een aantal voorbeelden van de dashboards die later besproken gaan worden. En dan geef ik nu het woord aan mijn collega Steven.
Mark, dankjewel. Mensen, goedemorgen. Op deze regenachtige dag in Nederland. Welkom, we vinden het leuk dat jullie deelnemen aan dit webinar. Dit is ontstaan uit de samenwerking tussen Quistor en Oracle. Zelf ben ik verantwoordelijk vanuit Oracle voor het healthcare segment. En zien wij in de samenwerking tussen Oracle en Quistor een aantal mooie samenwerkingen ontstaan met klanten. En zoals je al op het scherm kan zien, worden wij vergezeld door een speciale gast vanuit Zweden. Die zal dadelijk het verhaal doen in het Engels. En ja, wat je gewoon ziet is dat het mission statement van Oracle is dat wij willen onze klanten, onze partners, mensen helpen met het zien van data in het nieuwe licht. En daar gaan we het later ook verder over hebben. Dus wat we vooral willen vandaag is zoveel mogelijk in de praktijk. Dus er zal een hoop hands-on getoond worden. Dan mag hij naar de volgende.
Yes. Oh,
begint.
Een korte toelichting. Dit webinar is gefocust op de gezondheidszorg. Vele instituten in Nederland binnen de gezondheidszorg zijn aanbestedingsplichtig. Dat betekent dat zij natuurlijk heel veel werk hebben bij het bereiden en het opzetten van tenders. De Europese Unie ziet het belang van cloud computing. Daarom hebben ze het OCRA framework in het leven gebracht. Het OCRA framework staat voor Open Cloud for Research Environments Framework. Dat betekent dat zij het eigenlijk makkelijker willen maken voor instituten om gebruik te maken van cloud computing technologieën. Nou, ze hebben daar voor elke land een organisatie neergezet, of die was er al, die eigenlijk dit framework moet waarborgen. In Nederland is dat SURF, voor de meesten wel bekend. En tijdens de aanbesteding zijn alle vendoren die daaraan meedoen gecheckt op een stukje compliancy en ook op hun pricing. En voor elk land is daar een exclusieve partner voor gekozen. Nou, in Nederland, u raadt het al, is dat Quistor voor Oracle. Zodoende dat wij ook een intensieve samenwerking hebben, niet alleen binnen het framework, maar ook daarbuiten. Dus ja, weet dat dit framework bestaat. Het is echt gemaakt om gemakkelijk cloud adoptie te kunnen ondersteunen en dus geen tenders te hoeven te doen. Dus als er een tendergrens van €55.000, wat het geloof ik is per jaar, daar hoef je dan geen Europese aanbesteding voor te doen op het moment dat je gebruik maakt van dit framework. Steven?
Ja, dan gaan we over naar het belang of de waarde van analytics. U allen zal binnen uw instelling te maken krijgen of al te maken hebben met een behoefte aan informatie. We komen uit een tijd, 10, 15 jaar geleden, waar de informatie of de dataordening centraal werd geregeld. Maar steeds meer en steeds vaker hebben wij sneller behoefte nodig aan informatie. En per projectgroep, per team, per eenheid heb je weer een andere informatiebehoefte en ook een andere snelheid. Nou, dat vraagt van organisaties dat ze het BI-model wat zij gebruiken anders gaan inrichten. De organisaties worden steeds meer data-gedreven aangestuurd. En je wil ook steeds meer niet alleen analyses doen op basis van data naar het verleden, maar je wil ook een stukje predictive doen. Waar gaat het naartoe? En wij denken ook samen in de samenwerking met Quistor dat wij u als instelling kunnen ondersteunen, zowel op het stukje analytics naar het verleden toe, maar ook in het stukje naar de toekomst toe, middels het inzetten van diverse machine learning en AI technologieën. En vandaar dat wij ook zullen vragen, of in ieder geval hopen op een nadere samenwerking na dit webinar, om daarover te kunnen sparren.
Dankjewel, Steven. Nog even een korte huishoudelijke mededeling. We hebben een chat aan de rechterkant. Er zijn er vragen, schroom ze niet om ze daarin te stellen. We zullen ze naar alle waarschijnlijkheid aan het einde van de meeting gaan behandelen. Mocht er tussendoor iets zijn, dan kan dat ook in de chat weergegeven worden. We gaan nu over naar de demo. So I'm going to hand over the word to Navid. Navid, welcome. Please share your screen. And,
okay,
take it away.
thank you. Okay, so let me get all the technical stuff up and running. So you should be able to see my screen on full screen now, correct?
Correct.
Okay, great. So hi everyone, my name is Navid Khan. I'm part of the specialist team in Oracle regarding analytics and AI. And I've been working at Oracle for approximately 8 years and covering specifically the AI and analytics domain predominantly of my time. And today I would want to present a bit of an innovative way of how analytics, AI, and machine learning can work from a healthcare perspective in this case. Now, the technology can, of course, be used for any industry for different use cases like fraud detection, predictive maintenance in manufacturing, providing the next best offer in retail channels and stuff like that. But we will be focusing here from a healthcare perspective and just to give you an idea of how the technology could work. So just to give you a bit of a background, we will be focusing on breast cancer analysis. And there's a lot of things happening here. Breast cancer is like top 5 type of cancerous types that is affecting a lot of the population around the world. And there's a lot of stuff happening within breast cancer from an analytics and AI perspective. And if we look into some of the work that has been done, it has been shown and proven that AI and analytics have a really effective way to increase efficiency from different angles when it comes to healthcare. It can be anything from detecting breast cancer tissue in an early stage, using AI to detect when they are looking at the X-ray images or MRI images from the breast cancer tissues. And as I mentioned, early stage detect where the cancer tissues are, and then be able to early proactively take care of the patients and thereby increasing the chances of the patient surviving. So there's a lot of stuff happening here, and I'm going to show you a couple of examples of how that is done using Oracle technology as an example. Just before I start, so this is, for example, a research that's been done in Australia. So what they were looking into, they were doing a kind of like a blind test, you could say. So they sent a couple of mammogram images to 6 type of specialist radiologists, and they were looking at the same time in parallel using AI to try to detect if there's any cancerous tissue here. And a couple of things that was noticed was, some of the doctors missed a couple of the images, that there was actually smaller cancerous tissue within all these images. And the point here is that, an algorithm or AI model, they never get tired. There is no human factor that comes into place. It can be running 24 hours a day across a huge amount of data, meaning a huge amount of patients, and covering basically the whole world, if you like. And one of the things that they noticed is the first, they were missing a few using the algorithm. But the second part was, it's not about replacing, but enhancing. So what I mean by that is that how these two things, when it comes to the specialist, together with the AI models, how they work in hand. So for example, there was another study showing that they were using the AI model to somehow prioritize which patients are most crucial and need to see a specialist now, so they could somehow prioritize among all the patients. So that was what the model was doing, not necessarily just detecting if it was a cancerous tissue or not, but helping out the doctor to focus on which one seems to be most crucial when it comes from a time perspective. Now, what I'm going to do today is I'm going to present and demo a lot of this stuff to show you some examples of how Oracle technology can help. And in this case, from a breast cancer analysis, as I mentioned, the same technology is and can be used across multiple industries, as I mentioned earlier, but we will be focusing from a healthcare perspective here. And what I have is public data. So I've been using a public data set called Wisconsin Breast Cancer Data Set. So you can actually Google that and you will see what type of data that exists. And to showcase how analytics and AI can help from different perspectives within breast cancer analysis. And these different perspectives are from these angles that we will look into in the demo. So we will kind of see from a high level perspective. So that could be someone who is responsible for the whole oncology department, like an executive level person, looking into what type of biopsy test we do when we are looking into a sample of the tissue, for example, how much did that cost, how many patients did we declare as malignant cancerous or benign cancerous, which method did we use, and what was the cost and effect of that. So more of a high level perspective, what is happening when it comes to our healthcare system, specifically for breast cancer. And then is the business analyst perspective. So that's a bit of someone who is responsible for looking at the tissue samples, for example, and test results and see what have we done and what is the actual result of the biopsy test. Are they cancerous or not? And then we will see from a data science perspective. So that is looking at from a deeper level, looking at the actual image itself and try to using AI to determine where is the cancerous tissue on the actual image itself. Okay, so we will have, let me go back. So this is from three perspectives, so an executive level, business analyst perspective, and a data science perspective. So we will look at the breast cancer tissue cells, looking at from a hospital view. We will look at the cancerous tissue, looking at the biopsy test results, and then also use the data science part, looking at the images to try to analyze the image itself, looking at where is the cancerous tissue. We will be using, so this is a bit of a flow. So we will have information coming from different systems, so health record systems, biopsy systems, the imagery system that looks at the breast cancer tissue and actually looks at the image itself. Integrate all that, we will store it in Oracle Cloud, and then use two predominantly solutions, basically. We will use Oracle Analytics to visually look at the whole result and the whole overview of the hospital, what type of biopsy test results we've done, how many patients we received, and so on. And then we will use the AI tools within Oracle Cloud to try to physically look at the imagery of the breast tissues and locate where does the cancerous tissue reside in the image itself, so detect them in an early stage. So with that, I'll actually jump over to my demo. So bear with me 1 second. So are you seeing my demo screen now? Can someone confirm? Okay. Okay, great. So this is looking at from a high level perspective. So what I'm seeing here from a hospital perspective, what is happening? So I see here number of patients we received in total. I can see things like what type of scans we've performed. So mammography, for example, here. We can see ultrasound. We can see CT scan. So this is looking at what type of diagnosis have I done and how many patients have I done it on. So on a high level view, understanding from a hospital perspective, to see also what is the cost for that, which we can drill down into further on. I can also see from all the patients that I've been analyzing and diagnosing, how many of them have I detected in an early stage? So stage 1 is in an early stage of the cancerous tissue, while stage 2A, for example, is when the cancerous tissue has spread across other tissues and actually created metastasis and spread thereby. So I want to see the ratio, and what I want to do is try to detect as an early stage as possible to be able to do something about it, basically. What I can do there is as I can see the biopsy test results. So when I take a biopsy test from the cell structure, I can see things like nuclear size, cell membrane, the perimeter size of the nucleus. So all of these things are interesting because they typically tend to be different between benign and malignant cancerous tissue, as an example. And what we're seeing here are the different metrics, as I mentioned, so smoothness, compactness, perimeter size, and then we're comparing between benign and malignant cancerous patients. Each dot then represents a patient in this case. So we can quite quickly, with just giving a glimpse with the eye, that there seems to be some metrics that seem to be different between benign and malignant. So for example, the compactness of the nucleus, that seems to be a bit different if I just compare these two. While if I look at the smoothness of the nucleus, they seem to be quite similar. It doesn't seem to be any difference between a benign and malignant cancer cell. Other things like the perimeter size of the nucleus, that is also an indicator that they seem to be different between a benign and malignant. So this is a way to look, how is it different from a benign and malignant cancerous tissue, and where should I focus my time on, basically, to analyze this further. This is looking at it from a visual way, and we will go into a bit more deeper of how we can analyze this further. I can also do some type of real-time reporting. So this means that when all these new patients coming in, how would I be able to track the trend and see in real time what is happening and what type of tests are we doing? So for example, here, it is going basically week by week, just simulating real-time data. But in actual, it will be, changing each hour, not each week, as an example. But this is looking at the data, and I can see, for example, during a specific week, a lot of it was CT scans, and then the next week it was ultrasound. So just seeing what is the trend and how is it changing during time. We can also see here, for example, the different stages. So how early are we detecting the patients in an early stage? And my goal is obviously to have the stage 1 number of patients really high. And what I don't want to have is so high on the stage 2A, because that means that we detected the patient's cancerous tissue in a late stage and a lot of damage has been done, for example. I can see the data from a different perspective as well. So this is looking at from, you could say, a graph perspective. And graphs is pretty nice to visualize, to see relationships between different metrics. And I'm not going to focus a bit in detail in this, but it's the same concept going through week by week. And then if I enlarge one of these, for examples, so this is looking at different scenarios. I can see I have a benign cancerous tissues. What type of X-ray have they done? Was it a CT scan and so on? And this is changing now week after week. And the interesting part is the line thickness. So the thicker the line is, the more that type of scenario is occurring. And the color of the line, so the darker it is, the more patients we have on that scenario. So what we actually want to do here is we want to see all the lines that are thick and dark, because that is something that is occurring quite frequently. And at the same time, the thin lines might be interesting as well, because it might be a scenario that we didn't think of earlier. But this is a way to see that there are some scenarios of cancer's type, what type of diagnostics we're doing, what type of imagery are we doing, and so on, that is quite interesting to see from a relationship perspective. So this is just a way to see it from a different angle, if you like. I can also see and do a bit more type of advanced analytics in the visualization tool, for example. So this is just one way to see it. And what I'm doing here, so if I enlarge one of these, I'm seeing the trend of the number of patients that we are receiving during different months, periods. And I can also visually right-click and say add statistics. So this is an easy way to trigger a bit more advanced statistics on the data to see, can I do something with the data set I have? So for example, doing a trend analysis or forecasting the number of patients that we will receive and doing this type of analysis based on the historical data. So I've done that, and the purple is then the historical data, and then the, you could say, blue type, neon type of color is the forecasted value to see what is the trend based on the historical data. So that is a way for me to plan my resources. Are we likely to receive more patients or not, for example? But it could be any type of metric, basically. This is just one example of how we can use forecasting, for example. So that is on the visualization side. So what I want to show you now is an example of, as I mentioned earlier, if you remember the scatter plot with all the cell structures, so things like nucleus size, cell membrane, and stuff like that. What I would want to do is I would want to look at historical data where we have taken the biopsy test results. We have then classified them as which of them were benign and which of them were malignant cancerous tissue. And then we want to take this historical insight, apply to new biopsy test results, and then be able in an early stage to predict, is it going to be benign or malignant cancerous tissue based on this historical data that we have. So this is a typical machine learning process. You typically train an algorithm on historical data of things that you know what happened and what was the, you could say, conditions. In this case, the conditions are the cell membrane structure. And then you want to apply it to new coming data, so new biopsy test results to predict what is the likelihood of this being malignant or benign, for example. So you typically do this in two stages. One is the training phase, where you train an algorithm based on this data, historical data. And the second is the apply phase, which means you apply the model to new coming data. So I'm just going to explain and show that as an example. So here we can actually create a bit of a type of data flows, if you like, and create, you could say, easier type of ETL, so meaning transformations. You have some data, you want to transform it in different ways, and then you store the data as a bit more transformed for your use case. In this case, I want to classify if it's benign or malignant. So I see here the data that I've had earlier. I saw the patient, so each row is representing a patient. I saw what was a diagnostic. So in the beginning, there's a lot of malignant. We have benign as well here, as you can see. We have the conditions of the cell, so structure, perimeter, size, and so on. And then we want to train an algorithm, and then we have the possibility to select different algorithms. So there's different use cases, which one you can try out different algorithms to see which one performs the best. But if you're more comfortable in machine learning, you would maybe prefer one because you've tried it out as an example. But this is different algorithms you can do. And the objective is a so-called two classification prediction, meaning it's either benign and malignant. That is our objective, to classify it when new coming data comes. So this is the target. Target means what is the column that I want to predict. In my case, it's diagnostics, benign or malignant. And then there are some settings for the algorithm, which I won't go into detail, but being able to tune the algorithm. I save the model, and the next step is apply. So if I go back here and open this one, so then I have new coming data. So this is new data that I haven't predicted. And then be able to select apply model. So it exists here in the same way. So we had the training that we did earlier. Now we want to apply the trained model. And once we've selected that, we can then select which model do I want to use. So as you can see, I've done different models for different use cases. The one that I want to do now is the cancerous tissue, so VBCD. So that stands for Wisconsin Breast Cancer Diagnostics in this case. And then I want to predict a value, meaning is it benign or malignant? And then I also want to give a percentage calculation based on how sure am I of this prediction. And then we can create a report on this. So the data that we created, we used a data set from historical data. We used a new data set from the incoming data. We trained the model, and then we apply the model for the new coming data. And then we can look at the model itself and see the model itself was 89% accurate. So 89% of the cases we predicted correctly. We can also see a bit more into detail how we predicted. So in this case, the Y column here, or the Y angle, is the predicted value, and the X axis is the actual value. So this is called a confusion matrix in AI or machine learning. And we can actually see 65 of the cases, they were in fact benign, and we classified them as benign. And 36 of the cases, they were malignant, and we also classified them as malignant. But since AI isn't, bulletproof, it's still a prediction, but it's really accurate prediction based on data. So there's also some misclassifications, but then we can check it out and see, can we optimize this model and tune it a bit more for my use case? So now we've done two things. We've analyzed the hospital data from a high-level perspective. What is happening? What are the type of diagnostics we're doing, and so on, and how many patients are we receiving? We have done the AI approach without any code, may I add. So it was all visit-based, but being able to do a bit more advanced predictions based on these biopsy test results we have on the cellular level, and be able to predict which patients are benign or malign. But the next stage would be to, how would I then implement this into, for example, a journal system? So I would want this to be a real-time scoring, meaning that every time someone have done a biopsy test, and I can directly then see when I open the journal, those information or that information of the biopsy test would automatically be sent to the model, to the machine learning model, predict what is the likelihood of benign or malign. And then in the journal, it should pop up that this patient is likely to be, or the images that we've taken are likely to be benign or malign because of these factors. So that's what I would want to do, integrate that into a system. So just to show you an example of how that could be done. So let me log into my environment. Okay, let me show it in another way, basically. So I'll do it like this instead. So basically what I want to do is I want to send the same data that I had, sending it to the database, and then be able to look at the parameter that I had earlier. So it's actually the same thing. The only difference is that this will be running in real time all the time. So I'll show you that in my environment as I had earlier. So if I go back here, looking at this, so this is what it will do, basically. The only difference is that I will be sending this to the database. So I'll saving this and saving that into the database. And then this will be running all the time, the same schedule, but it will be pushed to the database. So I can save this model, save it, and then select where to save this flow. And then this, instead of this running in my analytical tool, it will be running in the database, because then I have scalability, performance, and all that. And once that's done, the result will be shown here in real time. So I will then see all of this stuff popping up in real time in my dashboard. And so as you can see now, it's not updating because it's not coming from the database, but once it's done, it will be automatically updated all the time in this case. The last type of scenario, so now we've kind of done it from two ways. So the first one was looking at the biopsy test results based on the values itself. So meaning like cell structure, nucleus size, and all that stuff, and try to determine based on these values which is benign or malign cancerous tissue. The second stage was that doing exactly the same thing actually, but sending it to the database because of performance, and I want that real-time scoring based on new coming data. The second or the last part is, instead of looking at the parameters like nucleus size, cell membrane and stuff, I want to actually look at the image itself, the physical image. So that's basically called image detection. And that's what I want to do here. So what I'm actually using is Python code and using stuff like TensorFlow. So TensorFlow is basically a code framework to do image detection analysis in this case. And what I want to show, so I won't go through the whole code, but basically I'm using a specific algorithm which is called neural network. So that's a pretty popular algorithm used for different type of use cases for image detection. And it has also been used a lot for breast cancer analysis to look at the breast cancer tissue and detecting where on the physical image the actual breast cancer tissue relies. Because as you remember earlier, we couldn't see exactly where in the tissue it was a cancerous tissue. We could only see that from the biopsy result, there is a cancerous tissue somewhere, but not locating it exactly where, but that's what we want to do in this case. So I'll go through and show you a bit here. So this is an example of normal tissue, just as an example, and then I have cancerous tissue, and I want the system to then learn based on these images, how does a normal tissue look like and how does a cancerous tissue look like, and then send again the model that I've trained on to new coming images to detect where it relies. So it's kind of the same concept as earlier, but now I'm looking at the image itself and not just parameters of things like nucleus size and so on. So if I go down, I'll show you. So these are basically some stats of the image itself. So for example, here of percentage-wise of all the images, how many of the images, so if you imagine that this is an image, how big of an image was a cancerous tissue? Was it the whole image itself or just a small portion of it? And you can see here, but it basically means that of all the images, where 20% of the image was cancerous tissue, that's the most type of images. But then we have some images where almost the whole image itself was cancerous, but it's not as many. So typically on an image, based on this data that I've had here, 20% of the image was actually cancerous tissue. The rest of the image was healthy tissue, as an example. So now I'm going to go down, and this is the part which is quite interesting. So this is now, I am creating the AI model or the image detection model. So it's called neural network, and the specific one is called convolutional neural network. Basically what it means is that it's looking at the image itself and step by step looking at each, you could say, pixel frame, and looking at how does this actual frame look like comparing to the cancerous and non-cancerous tissue that we've learned on from historical data. So this is creating the model and training the model, basically. This is the training phase of it. And if I go down, this is then what the model has created. So typically a neural network, there's a lot of different layers. Each layer is finding something interesting in the image itself. That's kind of the high-level thought of deep learning or image classification, in this case, using neural network. And as I mentioned, each layer is fine-tuning the image and finding something. And I'm going to show you a little lower. So this is looking at the performance of the machine learning model. Basically, what you want is you want this curve to go as far up as possible here and then turn to the right. What it basically means is that I want to have as many true positive classification as possible and as few as false rated classification as possible. That basically means that if I took an image, I used the AI model to classify, is this benign or malign? If it classified it as a malign, and in fact it was malign, that means it's a true positive. But if I classified it as a malign, but in fact it was benign, then it was false positive, as an example. And as you can imagine, we want to basically have as many true positive as possible and as few false positive as possible. Thereby, the curve should be as far up here as possible. That means that the model is really accurate, basically. So if I go down, this is basically what it has done. So this is looking at one specific patient, looking at some images, and I have taken 2 images of a specific part of the breast sample. So as you can imagine, so what typically happens is that when you take an imagery of the breast tissue, it slices it up into several slices, and then looking at each slice of that image. That's basically how the CT scan works, go through the whole organ, if you like, slice by slice, and then taking an image, basically. And what if I go down, so this is what the algorithm then has learned. So I have different patients here, different parts of the breast cell structure, and somewhere here it relies a cancerous tissue in the image. So this is looking at the tissue sample, if you like. And then the algorithm, it has detected the gray dots in it. That's the pixels that we just classified as cancerous tissue based on this historical data. So that's the prediction that we've done, taking an image, test, taking that image, sending that to the algorithm, the neural network algorithm, and then it had spotted these pixels to be breast cancerous tissue, and then we can further investigate that. So that's how we've done using the machine learning models in this case. And if I go back, so what you basically seen a bit high level is from the hospital view, looking at the cancerous tissue, looking at the hospital view of type of analysis we have done, what type of stage they're within, and so on. I've also jumped into a bit on the machine learning side from the analytical tool. So basically from an easy way, if you like, how can we create the machine learning model without any code, but the visit based on these tissue sample that we had, looking at things like nucleosides, cell membrane, and stuff like that, and then be able to predict how many of these patients are benign or malignant cancerous based on that cellular data. And the last one, looking at not just the parameters like nucleosides and stuff like that, but actually taking the image itself, because as I mentioned, the image contains a lot more information. So taking the image, looking at the image, comparing cancerous image with non-cancerous, and then sending those images to the algorithm, and then be able to visually detect on the image itself, not just as classified if it's malignant or benign, but actually also locating in the image itself where it resides. Now, once we have done that, so the system itself then can be integrated, as I mentioned, to any type of application. So it could either be integrated directly on the CT scan. So when I'm taking the images here, seeing the breast tissues or the whole image itself using a computer tomography, I would want it to also show me where the cancerous tissue resides inside the application directly as well. So that's one way of it. I could also then integrate this into the electronic health record. So every time a doctor looks at the record system, when the things like biopsy test results have been taken, it could be also showed as a frame somewhere here that the likelihood of this sample being a benign or malignant cancerous tissue is 98% or whatever, and also giving me the image of where exactly do we predict that this cancerous tissue is residing at the patient site, as an example. So this is different ways of how this could then be integrated into third-party applications, basically. So this is the example that I just showed, but this is a bit more from a theoretical side of what we have actually done. So as I mentioned, we were taking the image, storing the images in the Oracle Cloud platform, using our data science tools to be able to analyze the images, and then creating. So this the network you see, that's typically an architecture of a neural network. So basically it takes the images and then sends it through, you could say, some minor calculations to find exactly where the breast cancer tissue comes in. So it's basically the same way here, as you can see. This is from our real journal system, so used in the US. So they have been using AI into their CT scans, as an example, and then we can see it plotting out where do we believe there are some cancerous tissue. It's also giving you a percentage-wise a metric saying that 97 or 98% accuracy. So same thing that we did in the tool, as an example. So this is a bit of a summary of what we did on the data science side. So taking the images, storing the images, and then providing, sending these images to the model to train the model based on which one was cancerous and not. And then, this is basically the setting. So if you're familiar with AI and deep learning, there are a lot of different type of architecture in the network, and you can play around and try different architectures. That means that how many layers do I want to have? Typically, if they're very complex, you could say conditions or complex images that we want to use, it could be interesting to have a higher amount of layers to find details, basically. That's a high-level explanation, basically. And then we can evaluate the model. So this is showing me then the model accuracy curves. So basically what happens that if I train the model with new data, more data coming in, tuning the model, then the accuracy, as you can see here, goes up during time because of the new inputs and tuning that we've done. And this is typically what's interesting, because this is a iterative process. It's not a one-time thing and then everything is working. You typically iterate and evolve or evaluate the model and then evolve the model based on new data and new parameters and new things that you learn. And that's quite a common way in machine learning in general, that you iterative approach the challenge and work with it. So what I want to show is a bit more from a innovative way. So there are some things called biomarkers. Biomarkers is basically, you could say, another way to indicate if you have a specific type of disease or not. So it's, other things can be affected by the disease you have. In cancer, there has been some research that has been developed that actually the teardrops that a human being develop and keeping the humidity in a certain level of the eye, basically, so it doesn't dry up, that actually includes some levels of different substance. And if you take that substance, you can actually reverse engineer, if you like, to see how likely is it that you are cancerous or not, from a breast cancer perspective. So there was some research done in Abu Dhabi, actually, and they found out that biomarkers could be one way, a quick and easy way to indicate that is there any likelihood of you having some type of breast cancer tissue. And it was like an easy way. It was a cost-effective, but at least a first step to investigate further. And then they were doing the mammography and stuff like that. But that was quite an interesting way. And what they figured out is that the teardrops, it consists of a lot of different stuff. So salt levels, and sweat levels, and water levels, and also fat levels, actually, but in a liquid form. So there's a lot of substance in a teardrop, and they found that all of these things joined together can be an indication for cancerous tissue or not, as an example. So this is what they basically did. So they had a device, and you basically picked up the teardrop, and it's actually more, so there was a lot of proteins that are an indicator for this. So it was around 1,500 protein types. So it's a lot of protein that actually is, you could say, left out from the tear, if you like, from the body. There are a lot of lipids, so fat types in the teardrop, water, salt, and mucus levels. And all of these things that were joined to create some type of AI model. So they had these indicators as input, and then putting it into an algorithm, and then finding at least a first prioritization that which of these patients are likely to have cancerous tissue or not. And the interesting part was that the device itself, it was really cost effective. So it cost around this specific plastic device that picks up the teardrop and then stores it on a paper. It cost around $2 to produce per device. The thing that is more advanced is then taking that sample and to sending it to a lab. But this was a really easy way to get the first analysis and a cost-effective way to then send it to an algorithm later on. So they took the sample from the teardrop, the values that existed from the teardrops, sent it to a deep learning algorithm, which then predicted, are you likely to be having a cancerous tissue or not, as an example. So this was a bit of a summary here. So just to show you a bit what we were looking into, looking from a high-level perspective, analyzing the hospital view, looking at what type of investigations we've done or biopsy test results we've done, how many patients were benign or malignant cancerous. We were also looking at the sample tissue, visually speaking, looking at the cell structure like nucleus size, cell membrane size, comparing them visually in an easy way to see which one of them were aggressive and non-aggressive cancers, to see is it the cell nucleus size or is it the cell membrane that is an indicator? We were then also using the machine learning side to be able to look at historical data and then predict if it's likely to be cancerous or not based on these parameters like thickness and cell membrane size and stuff like that. And then the more sophisticated one, we were then also using the deep learning type of algorithms, which is looking at the image itself, not just at the data stored regarding perimeter size, but also looking at the whole image itself. Things like color and stuff like that could be a factor, and then be able to detect where physically the cancerous tissue is located, not just indicating if it's cancerous or not, but also where it exists. And we basically saw it from 3 different levels. So from an executive level that I showed you earlier on the dashboard, a bit more from an analyst level, so someone who actually looks at the tissue cells itself and detects, so for example, an oncologist, for example, and then also from a data science perspective. So someone who is a bit more from an AI and machine learning expert, how can they join forces with the oncologist to create these machine learning models that can be easily detecting cancerous tissue and work as some type of prioritization. So as I mentioned earlier in my introduction, it's not about replacing, it is about enhancing, that we can join forces and work together to quicker indicate or figure out where we should focus on when it comes to the number of patients having breast cancer or not, as an example. So that was it from me. Hope it was interesting and you got excited of seeing Oracle from an analytics and AI perspective in a different way. Now, as I mentioned, this is from a AI and machine learning perspective for specifically breast cancer, but the same technology, the same concept as I showed the slide here. Using the technologies can be used for a lot of different use cases like fraud detection in bank and finance, or in retail using these technology for next best offer in a web page, for example. So there's a lot of different type of use cases, but the common thing is the technology of storing data, integrating data, and then using AI and machine learning to be able to report and detect what is going to happen based on different conditions. So with that, I would like to hand over the word and thank you so much for me.
Dames en heren, bedankt voor het bijwonen van dit webinar. Ik hoop dat jullie een helder inzicht heeft gegeven in wat Oracle Analytics Cloud voor jullie kan betekenen. En indien jullie vragen hebben, mogen jullie natuurlijk altijd contact opnemen met mij of met Steven Rijgersberg. Onze e-mailadressen staan op het scherm. Nogmaals bedankt en succes.